Hello everyone, welcome to this video on what is transfer learning by Intellipaat. Do you guys know GPT-4, the model that is running ChatGPT, is also a transfer learning model? This fact itself should be enough to understand how important the concept of transfer learning is in the context of AI. Today, with this particular video, we are going to do a thorough theoretical and technical exploration of this deep learning concept. We will understand what transfer learning is with the help of an example. We will explain how this model works, why should you use it, and steps to use it. Towards the end, we will also cover the different types of transfer learning models out there. But before we do that, make sure to enable both the subscribe button and the bell icon for Intellipaat YouTube channel so that you would not miss out multiple updates coming from our side.
What is transfer learning? Let's start with an example to learn what transfer learning actually is about. Meet Alex and Becky. Alex was always into indoor games and Becky was more into physical activities. Growing up, Becky joined a football club and Alex was more into studies. One day, Becky challenged Alex for a football match at the school. Let's look at how both of them prepared for the same. Since Alex didn't have any idea about playing football, it took him 3 months to learn to play football and another 15 days to practice for the match day. Now, Becky skipped the process of learning football because she was already trained in how to play football and she just focused on practicing for the match day. Now, Becky, who is already trained in football, represents transfer learning. Transfer learning involves taking a pre-trained model, in this case Becky's prior knowledge of football, and fine-tuning it for a specific task like practicing for the match. She already had the foundational skills and experience, so she needed only a short time to adapt and practice specifically for the upcoming match. Alex, on the other hand, represents a traditional machine learning model, initially focused more on studies, different from a model which already has basic knowledge. Alex took 3 months to learn about football, similarly like a machine learning model that learns from scratch. After acquiring the basic knowledge, he spent another 15 days practicing, that is, fine-tuning his knowledge. However, since he started from scratch, it took more time for him to get ready compared to Becky. Now, transfer learning enables us to transfer knowledge from one task to another, providing a head start in training deep learning models and improving their performance on new and different tasks. Transfer learning is a technique in deep learning where knowledge gained from solving one problem is applied to another related problem. It also allows us to reuse pre-trained models and their learned features to tackle new tasks, even when we have limited data for the specific task at hand. The idea behind transfer learning is that the early layers of a deep neural network learn low-level features like edges, textures, and basic shapes which are generally applicable to many different tasks. By using a pre-trained model, we can benefit from these learned features and avoid the need to train a model from the ground up. How transfer learning works? Now, this diagram shows a pre-trained CNN on the left side. This CNN has already been trained on a massive data set of images like ImageNet and has learned to extract low-level features like edges, textures, and shapes. Now, the extracted features from the pre-trained CNN are then transferred to the transfer parameters section. These features are like building blocks that can be used to learn more complex features for the new task. On the right side, we have the fully connected CNN specifically designed for the new task. This could be anything from classifying different types of animals to predicting medical diagnosis for X-rays. Now, the pre-trained features are fed into the new CNN, but the final layers of the pre-trained network are discarded. These final layers were specific to the original task and wouldn't be helpful for the new one. Now, we add new layers. New layers are added to the top of the transferred features. These new layers are specific to the new task and will learn to combine the pre-trained features in a way that's relevant to the new problem. The entire model, including both the transferred features and the new layers, is then trained on a data set of images for the new task. This fine-tunes the weights of the new layers and helps them learn how to interpret the pre-trained features for the specific task. Let's have a look at mathematical intuition. Now we have a domain D consisting of elements X and their marginal distribution is Px. Now the feature space refers to the space or set where the input data or the features exist. It represents the characteristics, attributes, or variables that define the data points. For instance, in image processing, the pixels of an image could be features, and in natural language processing, words or embeddings could be considered features. What is marginal distribution? The marginal distribution, which is P of X, represents the probability distribution of the features or inputs in the given domain. It describes the probability of occurrence or distribution of these features across the dataset. Mathematically, transfer learning aims to find mappings or relationships between the source domain and the target domain. The intuition lies in understanding and utilizing the similarities or relationships between these domains, allowing the transfer of knowledge, representations, or learned patterns from the source to the target domain. So, by feature extraction, what we are doing is the pre-trained model is typically using a fixed feature extractor. The input data is passed through the model's layers and the activations or outputs of certain layers are extracted as the learned features. In transfer learning, this allows the reuse of valuable learned representations from one domain to improve learning or performance in a related but distinct domain. Often, this requires less data and computation than training an entirely new model from scratch. Now we hop on to repurposing process. Now, repurposing process might involve various strategies like adjusting and updating specific paths or all the pre-trained models' parameters, to freezing layers, to adding new layers. We keep certain layers or parts of the pre-trained model fixed while modifying the others to make our data specific with new layers or modules that is more specific to a new task. Now we have a diagram which shows a source domain, which is the original task, and data set the pre-trained model was trained on. This example shows ImageNet as the source domain. Now a pre-trained CNN model trained on the source domain data is shown. This model has extracted valuable features from the training images. The initial layers of the pre-trained CNN are responsible for feature extraction. These layers are often frozen during transfer learning, meaning their weights are not updated during training on the new task. So they remain constant. Now the right side of the diagram depicts the target domain, which represents the new task and dataset you want to apply the pre-trained model to. This could be any domain with data visually or structurally similar to the source domain. Now we have the classification layer. The pre-trained model usually has a final classification layer specific to the source domain task. This layer is typically removed or replaced with a new classification layer designed for the target domain task. A new classification layer is added on top of the extracted features. This layer is specifically tailored to the specific categories or outputs which are required for the target domain task. Then happens the training the new model. The model with the frozen feature extraction layers and the new classification layer is then trained on the target domain data. Now, this helps the new classification layer learn how to interpret the extracted features for the specific task of the now target domain. The outcome of the transfer learning model is to get the target domain data, but benefiting from the pre-trained knowledge of the source domain. Now, this can lead to faster training times and potentially better performance compared to training a model from scratch on the target domain alone. So, the difference between this diagram and the earlier diagram is this variation focuses more on freezing the feature extraction layers and replacing the final classification layer instead of adding new layers on the top. Now, why should we use transfer learning? Transfer learning offers several compelling reasons to use it. So first and foremost, instead of starting from scratch and collecting vast amounts of data, we can use these pre-trained models as a foundation for our own tasks. These models This significantly reduces the amount of data required and speeds up the learning process. Another advantage of transfer learning is its ability to generalize well. By learning from a diverse range of tasks, the model gains a broader understanding of the underlying patterns and features in the data, reduces the training time. This enables the model to perform better on new unseen tasks and data sets. Moreover, transfer learning is particularly useful when we have limited data available for our specific task. So instead of training a model from scratch, which may lead to overfitting or poor performance, we get an improved neural network performance, which will fine-tune a pre-trained model to adapt to a specific problem. This saves time and computational resources while still achieving good results. Steps to use transfer learning. Now, transfer learning allows us to use pre-trained models and apply them to new tasks with limited data. So the first step is obtaining a pre-trained model. We start by selecting a model that has already been trained on a large data set for a specific task such as image recognition or natural language processing. This pre-trained model acts as a valuable starting point for transfer learning. Obtaining a pre-trained model involves accessing or downloading the model from a reliable source such as TensorFlow or PyTorch. Then we create a base model. When we create a base model, we start with the pre-trained model and remove the final classification layers. These final layers are responsible for making predictions specific to the original task the model was trained on. By removing these layers, we strip away the task-specific knowledge and retain the learned features captured by the earlier layers. These final layers are responsible for making predictions specific to the original task the model was trained on. By removing these layers, we strip away the task-specific knowledge and retain the learned features captured by the earlier layers. The remaining layers in the base model, often referred to as feature extraction layers, have learned to extract general features from the input data. These features can be useful for a wide range of related tasks. So then we can move on to the third step, which is freezing layers. When we have freeze the layers, it means that the weights of those layers will remain unchanged and not be updated during training. By doing so, we ensure that the pre-trained model's learned features which are stored in the frozen layers are retained and not modified. Fourth step is to add new trainable layers. Add new layers on the top of the base model that is specific to your task. These new layers will randomly initialize and will learn to adapt the pre-trained features and to your specific problem. Then we train the new layers. Train the model using your labeled data. Since the pre-trained layers are already frozen, only the new layers will be updated during this training. So these new layers are initialized randomly or with some predefined structure. During training, you only update the parameters, that is the weights and biases of these newly added layers, while keeping the weights of the pre-trained layers fixed. Now, this strategy allows the model to learn task-specific features from the new data set without losing the valuable knowledge captured in the earlier layers. Next, we move on to fine-tune your model, which is optional also. To fine-tune the model, we unfreeze the frozen layers, allowing their weights also to be updated during training. This enables the model to learn more task-specific features from the new dataset while retaining the valuable representation which was learned from the original task. Fine-tuning can be particularly beneficial when the new task is closely related to the original task, which was on which the pre-trained model was trained on. Going forward, we'll have a look on popular models which are trained using transfer learning. So, several popular models have been successfully trained using transfer learning. We will have a look at some of them. VGG16. The VGG model developed by the Visual Geometry Group is characterized by its simplicity and deep architecture. It consists of a stack of 3x3 convolutional layers with increasing depth and volume size, which is followed by a fully connected layers. So, VGG performs well in large-scale image recognition tasks, and the architecture consists of 16 layers, which is primarily stacked convolutional layers followed by max pooling layers and fully connected layers at the end. Now, VGG excels in learning intricate patterns but is computationally expensive due to its depth and the number of parameters. Moving on to ResNet 50. Now, ResNet 50 is a popular deep convolutional neural network. It is a deeper architecture with 50 layers. Its distinctive feature is the use of residual blocks, which allows the network to avoid degradation issues that can occur in very deep networks. These blocks contain skip connections, which are like shortcuts that skip one or more layers, enabling the gradient to flow more effectively during training. This makes it more effective for various computer vision tasks, particularly when dealing with very deep networks where degradation in performance might occur. Finally, we have BERT. This is a very powerful language representation model which is developed by Google. It implements transfer learning by pre-training on large amounts of text data to learn rich contextualized representation of words. In BERT, transfer learning occurs in two stages, pre-training and fine-tuning. During pre-training, BERT learns general language representations by training on massive text corpora. Learning to predict missing words within sentences bidirectionally. So for transfer learning, the pre-trained BERT model is fine-tuned on a smaller dataset specific to a downstream task, such as sentiment analysis or question answering. That's all we have for this video. I hope you got a good idea about what transfer learning is all about. If you found this video helpful, please give it a thumbs up and share it with your fellow mates. Also make sure to subscribe to our YouTube channel so that you don't miss any updates coming from our side. Thank you for joining us, and we wish you very success on your transfer learning journey.
Just a quick info, guys. Intellipaat offers machine learning course in collaboration with IITM Pravartak. Through this course, you will learn various algorithms and machine learning techniques such as supervised, unsupervised learning, natural language processing, and much more from the IIT Madras faculty and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given below in the description. Without a doubt, this course can set your career to new heights. So visit the course page given below in the description and take a first step towards career growth in the field of machine learning.